Alright, let's go. Number 7. The impossible early galaxies. In July 2022, NASA released the first deep field image from the James Webb Space Telescope. Astronomers around the world celebrated the unprecedented clarity. Within months, that celebration turned into something closer to panic. Webb had detected galaxies that, according to every model of cosmology developed over the past century, should not exist. The galaxies in question appeared just 300 to 500 million years after the Big Bang. By every accepted theory of structure formation, the early universe shouldn't have had time to assemble anything this large. Stars need time to ignite. Gas needs time to collapse. Galaxies need time to form, merge, and grow. Yet, Webb was finding fully formed galactic structures with masses comparable to the Milky Way, existing in an era when mathematically they couldn't possibly be there. Astronomer Ivo Lab at Swinburne University led one of the teams that confirmed the impossibility. His group identified 6 candidate galaxies that contained as many stars as the Milky Way does today, despite existing when the universe was less than 3% of its current age. The mass density of these objects exceeded what the standard cosmological model predicts by a factor of more than 30. To put that in perspective, finding these galaxies is statistically equivalent to opening a single bag of sand and discovering more grains than exist on every beach on Earth. What makes this discovery particularly disturbing is what it implies about everything else. The standard model of cosmology, the framework that explains the Big Bang, the cosmic microwave background, the formation of structure, and the distribution of matter across the universe, depends on specific assumptions about how galaxies form and how quickly. If those galaxies are real, and follow-up observations have continued to confirm their existence, then something fundamental is wrong with our understanding of the universe. Some physicists propose that dark matter behaves differently than we believe. Others suggest the early universe expanded at a rate we've miscalculated. A few have begun quietly proposing that the Big Bang itself may need revision, that what we've called the beginning of everything may not have been the beginning at all. The implications extend far beyond a few unusual galaxies. If our timeline of cosmic history is wrong by hundreds of millions of years, every estimate of the universe's age, every calculation of its eventual fate, every map of its structure becomes suspect. We're not just looking at galaxies that shouldn't exist. We're looking at evidence that the universe has been hiding a different story than the one we told ourselves. Number 6, the cosmological constant problem. In 1917, Albert Einstein introduced a small mathematical term into his equations of general relativity. He called it the cosmological constant, and he later described it as the greatest blunder of his career. He was wrong. The constant turned out to be real, measurable, and responsible for the accelerating expansion of the universe, but its value, the actual number that governs how dark energy behaves, represents what physicists openly call the worst theoretical prediction in the history of science. Quantum field theory, the framework that describes particles and forces at the smallest scales, predicts a specific value for the energy density of empty space. Vacuum is not truly empty. It sees with virtual particles popping in and out of existence, each contributing to the underlying energy of reality itself. When physicists calculate what this energy should add up to, they arrive at a precise number. That number is wrong by a factor of 10 to the 120. This isn't a small error. This isn't a measurement that's slightly off. The predicted value of the cosmological constant differs from the observed value by a factor written as 1 followed by 120. To grasp the scale of this disagreement, consider that the number of atoms in the observable universe is approximately 10 to the 80. The discrepancy between theory and reality exceeds the total atomic count of the universe by 40 orders of magnitude. By every principle of physics we trust, the universe should not exist in its current form. With the predicted vacuum energy, space would either have ripped itself apart in the first instant of creation, expanding so violently that no matter could form, or it would have collapsed back on itself before stars ignited, galaxies, planets, life. None of it should be possible. The fact that you're reading this script means something is preventing the cosmological constant from having the value our best physics says it must have. What makes this paradox truly unsettling is that there's no agreed upon solution. Some theorists invoke the multiverse, suggesting that countless universes exist with different values of the constant, and we naturally find ourselves in one of the rare hospitable ones. Others propose unknown symmetries that cancel out the predicted energy. A few argue that quantum field theory itself, the most successful theory in physics, must be fundamentally incomplete. The cosmological constant problem isn't a minor disagreement between theorists. It's a 120 order of magnitude crack in the foundation of physics. Every time you look at the night sky, you're looking at evidence that something we don't understand is holding reality together. The universe is balancing on a mathematical impossibility, and no one, after more than a century of trying, has been able to explain why. Number 5, the matter that shouldn't be here. In the first instant after the Big Bang, the universe was a furnace of pure energy. As that energy cooled, it began to crystallize into matter through a process described by Einstein's most famous equation. Energy converts to mass, particles emerge, the cosmos begins to take physical form. But there's a problem with this story. Every particle of matter created in the early universe should have been accompanied by an equivalent particle of antimatter. This is one of the most fundamental rules of physics, demonstrated countless times in particle accelerators around the world. When energy converts to matter, it produces particle and anti-particle pairs in exactly equal quantities. There are no exceptions. There is no asymmetry in the equations. When matter and antimatter meet, they annihilate completely, converting back into pure energy. If the early universe produced equal amounts of both as our physics demands, then within microseconds of the Big Bang, all matter and all antimatter should have collided, annihilated, and left nothing behind but a cooling sea of radiation expanding into emptiness forever. That isn't what happened. Somehow, for reasons no one has been able to explain, matter survived. The universe today contains stars, galaxies, planets, and you. Antimatter has been almost entirely erased from existence, surviving only in trace amounts produced by cosmic ray collisions and laboratory experiments. For every billion antimatter particles that existed at the dawn of time, approximately 1,000,000,001 matter particles were produced. That tiny excess, less than 1 part in a billion, became everything. This violation has a name. Physicists call it baryogenesis, and despite decades of theoretical work, no one has produced an explanation that fits the evidence. Experiments at CERN's Large Hadron Collider at Fermi Lab in Illinois and at facilities in Japan and Italy have searched relentlessly for processes that could create this asymmetry. They found nothing sufficient. The matter-antimatter imbalance our universe requires is approximately 1 billion times larger than anything observed in particle physics experiments. Some theorists propose that unknown particles existed in the early universe and decayed in ways that favored matter. Others suggest that exotic interactions, undetectable by current technology, broke the symmetry during the first fractions of a second. A few have proposed that we live in a pocket of matter within a larger universe where vast regions of antimatter exist somewhere we cannot observe, separated from us by voids of pure radiation. The truly disturbing aspect is what this means for your existence. You are made of atoms that by the laws of physics should have annihilated 13.8 billion years ago. Every molecule in your body is a survivor of an apocalypse that should have left nothing behind. We don't know why matter exists. We don't know why we exist. The universe we inhabit is built on a violation of the very rules that brought it into being. Number 4, dark matter and the missing universe. In 1933, Swiss astronomer Fritz Zwicky was studying the Coma cluster, a vast collection of galaxies bound together by gravity. He measured how fast the galaxies were moving and calculated how much mass should be present to keep them gravitationally bound. Numbers didn't match. The galaxies were moving so fast that the visible matter in the cluster, all the stars, all the gas, all the dust, should have been completely insufficient to hold them together. By every law of gravity we understand, the Coma cluster should have flown apart billions of years ago. Zwicky proposed something that other astronomers initially dismissed. There must be dunal materia, dark matter, invisible mass, providing the gravitational glue that visible mass alone could not. His colleagues called it speculation. They were wrong. In the 1970s, astronomer Vera Rubin confirmed the impossibility on a galactic scale. She measured the rotation of stars in spiral galaxies and discovered that stars at the outer edges were moving as fast as stars near the center. This shouldn't happen. By the same physics that keeps planets closer to the sun, moving faster than planets farther out. Stars at the edges of galaxies should be moving more slowly. They weren't. Something invisible was providing additional gravity throughout every galaxy, holding stars in place that by visible matter alone should have flown into intergalactic space. The numbers eventually became precise and devastating. Visible matter, everything we can see and detect through any electromagnetic radiation, makes up approximately 5% of the universe. Dark matter accounts for roughly 27%. Dark energy fills the remaining 68%. We can detect 5% of reality. The other 95% is composed of substances we have never directly observed, never identified, and cannot explain. What makes dark matter particularly unsettling is the failure of every attempt to find it. For decades, physicists have built increasingly sensitive detectors, deep underground laboratories shielded from cosmic radiation designed to catch the faint signal of dark matter, particles passing through. The Xenon experiment in Italy, the Zeppelin detector in South Dakota, the Pandax experiment in China. Each one represents the most sensitive instrument ever constructed for its purpose. Each one has found nothing. Theoretical physics has produced candidate after candidate, weakly interacting massive particles, axions, sterile neutrinos, primordial black holes. Each theory predicted properties that detectors should have been able to identify. Each prediction has failed. We know dark matter must exist because galaxies don't fly apart. We know it has mass because gravity works. But every property we expect it to have, every interaction we believe it should produce, fails to materialize when we look. The implications extend to the foundations of physics itself. Some scientists have begun proposing that dark matter doesn't exist at all, that gravity behaves differently at galactic scales than Einstein's equations predict. This idea, called modified Newtonian dynamics, would require rewriting general relativity. Others suggest that dark matter exists in a parallel sector of physics, a shadow universe that overlaps with ours, but interacts only through gravity, populated by particles, structures, and possibly even forms of organization we will never directly perceive. Whatever it is, dark matter shapes every galaxy, holds every cluster together, and determines the structure of the cosmos itself. We exist within a vast, invisible scaffolding that we cannot see, cannot touch, and cannot identify. The universe you live in is mostly composed of something physics insists must exist, but has refused after 90 years of searching to reveal itself. Number 3, the proton's impossible stability. Every atom in your body contains protons. These positively charged particles sit at the center of nuclei, providing the structural foundation for chemistry, biology, and matter itself. According to grand unified theories, the most ambitious frameworks in modern physics, designed to merge electromagnetism with the strong and weak nuclear forces. Protons should not be stable. They should decay. The mathematics are clear. If the fundamental forces of nature merge into a single unified force at high energies, as theory predicts, then protons must occasionally undergo spontaneous decay, breaking down into lighter particles like positrons and pions. The predicted half-life varies depending on which version of the theory you accept, but most models predict proton decay within timescales between 10 to the 31 and 10 to the 36 years. Physicists built detectors to find this decay. The Super Kameo experiment in Japan consists of 50,000 tons of ultra-pure water surrounded by photomultiplier tubes deep beneath a mountain. The detector has been running since 1996, watching more protons than exist in any laboratory experiment ever constructed, waiting for even a single one to break down. Not one has decayed. The current experimental lower bound on proton lifetime exceeds 10 to the 34 years. This number is so vast that it defies meaningful comparison. The universe is 1.38 times 10 years old. The proton's measured stability exceeds the age of the universe by a factor of nearly 10 to the 24th. Every proton you possess has existed since shortly after the Big Bang and shows no sign of decay, despite our best efforts to catch even one violating its expected mortality. This stability creates a profound problem for theoretical physics. Grand unified theories don't simply predict proton decay, they require it. Without proton decay, the unification of forces becomes mathematically incomplete. The simplest versions of these theories have been ruled out by experiment. More complex versions remain viable, but each one must contort itself to explain why protons live so much longer than basic principles suggest. What makes this discovery particularly unsettling is the alternative interpretation. If protons truly are stable, if no decay process exists, no matter how long we wait, then one of two things must be true. Either